Hey everybody, welcome to my channel. This is Space by Jace. If you're new here, thank you so much for joining my channel. In a recent video, I talked about the Supernova expansion from Messier 1, the Crab Nebula. When I posted that video, someone suggested that I should compare my image to the 1950 image of the Crab Nebula by Walter Baade. In this video, I'm going to do just that, but first I want to talk about the life cycle of a star. As you may know, stars are massive balls of nuclear fusion. They are made up primarily of hydrogen, which is constantly fusing into heavier elements such as helium. I want to show you what that fusion process actually looks like. I made an animation so you can get an idea of what is happening in that nuclear fusion process. In this animation, you're going to see protons, neutrons, positrons, neutrinos, and the release of energy. You'll see hydrogen atoms fusing into the isotope deuterium. Deuterium will then fuse into helium-3, which will then fuse into the stable isotope of helium, helium-4. When you have enough mass gathered in one area, you end up with a lot of heat and a lot of pressure. That heat and pressure causes hydrogen atoms to combine with each other. They literally fuse together. When they fuse together, they create what's called deuterium, which is a heavier isotope of hydrogen. When this fusion happens, it releases both a neutrino and a positron. The deuterium isotope then fuses with another hydrogen atom to create helium-3. When this happens, there's an extreme amount of energy released. Two helium-3 molecules then fuse together to create helium-4. When that fusion takes place, it also releases two additional hydrogen atoms, which then go on to repeat the fusion process over and over. This is constantly going on in every star in existence. Just like the Earth, the Sun has many layers. Within the star itself, there's a constant battle between the crushing weight of the star pressing inwards and the energy from the nuclear fusion in the core of the star expanding outwards. While all the hydrogen is fusing into helium, there's a perfect balance between these two forces, and the star is relatively peaceful. Eventually, all of the hydrogen will fuse into helium. In a main sequence star like our Sun, this takes about 7 million years to happen. When it does, gravity becomes the stronger force, and the star begins to collapse in on itself. That additional pressure starts the next phase in the fusion process, which is forcing helium to fuse into carbon. This step takes a main sequence star about 500,000 years to complete. Once that is completed, carbon then fuses into neon over the course of 600 years. Neon fuses into oxygen within a year. Oxygen fuses into silicon within 6 months, and then within a day, silicon fuses into iron, and no more nuclear fusion can take place. This is when the star meets its death. Since there's no more nuclear fusion to keep the core of the star expanding outwards, gravity wins, and in a fourth of a second, the core of the star will collapse into a sphere roughly 6 miles wide. All stars will eventually burn through all of their available fuel through nuclear fusion. A lot of physics goes into a core collapse supernova, which I'm not going to go into detail on that right now, but the end result will be either a neutron star or a black hole, depending on the mass of the original star. The Crab Nebula was left with a pulsar, which is a type of neutron star. It is currently spinning at 30.2 times per second. The reason it is spinning so fast is because of the conservation of angular momentum. When you take all of that mass and pack it into such a small area, the rate of spin increases. This is just like when a figure skater tucks in their arms to spin very quickly. Anyways, getting back to the purpose of this video, in 1950, Walter Baade took an image of the Crab Nebula. I want to compare that image to Hubble's image from 1999, as well as my image from 2026. I found that image on the Palomar Skies blogspot back from an article that was posted in 2010. I first took the image into Photoshop and laid it on top of Hubble's 1999 image. By lowering the opacity, I could rotate it and change its size in order to align the stars as best as possible. I also took Hubble's image and laid it on top of Walter Baades' image. I aligned the nebula itself instead of the stars in this because I wanted to colorize Walter's image from 1950 since it was originally a monochrome image. I had a really hard time blending the two images together because the exposure levels were so different. I played around with it quite a bit in PixInsight, and what I ended up doing is pulling the stars from Walter's image, overlaying it onto the shrunken down Hubble image, and I'm going to show you both a monochrome progression of time as well as a simulated color version where the Hubble image has been reduced in size to match the actual size the nebula was in 1950. If you've made it this far in the video, thank you so much for hanging in there with me. I know that I am long-winded nature, I just really like talking about space. And now sit back, relax, and enjoy 75 years of supernova expansion. If you like what you saw in this video, please consider subscribing to my channel for more space-related content. If there's anything you'd want to see or learn about in future videos, please comment below.